Okay, so now I'm going to do an example of about computing curvature, so that you see it's more or less natural concept that does give you some quantitative notion of the bending of a curve. From last time, remember that curvature just magically appeared into the expression for the normal component of the acceleration, and it had this formula. It was the inverse of the speed, so 1 over speed times the derivative with respect to time of the tangent vector. So at least two things we would like to know is like that lines are with zero curvature, right? Because lines are not supposed to bend. And another natural curve is the circle, and we can actually find some interesting conclusions about what the answer should be in that case. So let's just do those two examples. So what's the case of a line? So on lines, it's very easy. The equation of a line, remember, is a point plus t times a vector, which is a velocity vector. So the r dt is just v, not surprisingly. And then the tangent vector, remember, is velocity over the speed. Okay, but the thing is, like, now this is truly constant because this was a constant vector, and so the derivative of the tangent vector with respect to t is 0, and hence the curvature has to be 0. So lines are without curvature, no curvature. Another example is a circle, the circle in the plane. This is more interesting. Let's say you have a circle of radius r. A parametrization of the circle, or like a formula for the equation of a circle, is r cosine of omega t, r sine of omega t. Omega here is a constant, which is known as the angular velocity. Okay. And so the velocity in this case gives you minus r omega sine of omega t, and then r omega cosine of omega t, and then the speed is r times omega. And so the tangent vector remember is velocity over speed. So when you divide this by this, you can cancel the r omegas. So you just get minus sine omega t cosine of omega t. And then the derivative of the tangent vector will be minus omega cosine of omega t minus omega sine of omega t. Okay? And finally, the curvature will be will be 1 over the speed. The speed was 1 over r. This will be 1 over r omega. And then the norm of this vector, right? The norm of this vector is just omega. So this is 1 over r. So a circle of radius r has curvature, constant curvature 1 over r. Okay, so that means that as you make the circle bigger and bigger, somehow you have to bend less and less in order to move along the circle. So, well, I mean, I won't be able to do it on the camera, but like imagine just traveling like along a circle. If you make the circle really, 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 really big, then that means that the curvature is really, really, really small. In a sense, as the r radius goes to infinity, the curvature goes to 0, and so as heuristically, like a circle of infinite radius is like a line, because lines have 0 curvature. Okay. On the other hand, as r gets really, really small, it means that you have to sort of bend faster and faster in order to keep moving along the circle. And so that's why you think as r goes to 0, the curvature starts to blow up and become infinite. Okay, so this is the notion of curvature for curves. There's like a notion of curvature for other objects like surfaces, which we won't discuss here, although I may make you watch an optional video about that. But the idea is that right, you can for example, the curvature on the surface of a sphere of radius r would be like 1 over r squared. And the idea is that you can sort of define a notion of curvature which does not require thinking of the surface as living inside some bigger space, meaning that there's like a way to sort of discover that your space is the space you live in is curved by just making intrinsic measurements on the surface and not having to sort of exit with a spaceship and see it from the outside and not realizing that it was curved to begin with. So if you have a debate with a flat earther, you can tell them about that you can actually measure the curvature of the Earth by just making intrinsic measurements without going to outer space. But I'll give you a video so that what I'm just saying makes more sense.